preserve directed paths. Okay, we got it. Okay, and some examples. So the most important example by far is a directed interval. It's just an interval, and you're allowed to go from left to right. All non-decreasing or increasing paths are allowed. And out of this example, we built all examples which will be interesting for us today, because our category is complete. The category of directed space is complete and co-complete. You can take, for example, products of intervals, and this way you obtain directed cubes. Or you can identify something in your spaces. For example, you can take an interval and identify endpoints, and what you get is a directed circle. It shows that also loops are allowed in our world. So these are not only partially ordered spaces. And our main character of our story are precubical sets. You see the definition already. So precubical sets are just sequences of sets, or it's a graded set. And these elements of the set represent cells of given dimension, and there are some face maps which tell which cell is the face of another cell. So these face maps are indexed by, well, the number of dimensions on one hand, and whether we take the upper face or lower face in our cube. And from this we can pass to geometric realization, which was also mentioned. From the purely combinatorial object, we pass to genuine directed space by taking true directed cubes and gluing them in a suitable way. And again, there are two examples. One is obvious one. You can construct a standard n-cube, which is a precubical set defined as here as sequences of zeros, ones, and stars, telling us whether we take the lower face or upper face of the whole interval in the given dimension. And this gives the whole family of interesting precubical sets, namely Euclidean complexes. Euclidean complexes are just subcomplexes of some standard cube. But not all precubical sets can be embedded into the standard cube. Another example, which is combinatorially very simple, but not so simple from the topological point of view, is the final precubical complex, the final precubical set, which has exactly one cell at every dimension. And I'm not able to give you a picture because you have one vertex and one edge, which makes a loop. And then you need to glue up a square by identify every face of this square with this loop. So it's something that cannot be easily embedded in any three-dimensional space. And then we go to the infinity. It's a very simple object because it has only one cell at every dimension. Face maps are defined in the only possible way. It's a final object in the categorical sense, but it's hard to see what's going on in geometry. So the main goal of the first part of my talk is to answer the question. We have some precubical set, we have two vertices of this precubical set, and we ask what's the space of directed paths which start at one vertex and at the other vertex. Namely, what's the homotopy type of this? So there is a sequence of results. The first result is obvious. When you start with a standard cube and look for the paths from the beginning to to the end, the final vertex, it's just contractible. But when you remove the interior of a cube, it's possible to show that the space of directed is homotopy equivalent to the sphere of dimension, which is, well, 2 less than the dimension of the cube. There is also the decomposition of your directed path space into length components, because to every path between 2 vertices, there may be given a length, and homotopic paths have the same length, and all lengths are integral, so your space falls apart into separate components connected to possible lengths. And I'd like to mention a model due to Martin Rausen, as the earlier results are also proven first by Martin, I believe. There is a prosimplicial model which allows calculation for Euclidean complexes to be more precise. If you have a cell and some rectangular areas removed in this cube, you can construct a prosimplicial complex which represents the homotopy type of the given space. And finally, I'd like to mention that you can get any space you want this way by taking a standard cube, removing some cells, and then looking for the space of directed paths. This way you can get any finite CW complex you wish. And okay. So, and I would like to tell you about one model for this space of directed paths. And we start with an observation how directed paths on precubical sets look like. So every directed path can be represented as a concatenation of segments, and every segment lies in some cube and is represented by a directed path on the standard cube, as on this picture. You have a directed path on the left, and this consists out of 4 segments on individual cubes. This presentation is not unique. Possible if you can check for the last part, you can check not the top cube here, the top interval, but you can take the whole cube, you will get another presentation of the same path. And we want to restrict to paths which are easier to handle. I will call them Tame paths. And Tame paths have presentations in which, when you travel through your cube, you have always travel from the very beginning to the very end. So, for example, this path at the left here is, you can see that, yes, is Tame because you travel first through this cube, then you travel through this cube from the very beginning to the very end, then you travel through this cube, and this is Tame. The path at the right is Tame, and it's not Tame. If you think if this path is embedded into a 3-dimensional cell with a cube, it's Tame because it just travels from the very beginning to the very end of this cube. If you regard this path as a path on the boundary cube, is no longer Tame because it doesn't go, it cannot be presented in a Tame way. And there is a theorem that for every precubical set, the inclusion of the space of Tame paths into the space of all paths is a homotopy equivalence, which I'm not going to talk about how to prove this. But I will talk about consequences. So all Tame paths lie in cube chains. Cube chains is a sequence of cubes such that the first vertex of the first cube is your starting point, and these cubes touch one to each other with the final vertex is identified with the initial vertex of the next cube. You have just such a sequence of cube chains, and this gives you nice presentation of the space of Tame directed paths. In the special case when our precubical complex is Euclidean, then the set of cube chains defines a cover of your space, and every element of this cover is contractible because the space of all paths traveling through your cube chain is contractible. Whenever you take two different cube chains and ask what the space of paths lying in both of them, the answer is it's either nothing or there exists a smaller cube chain which contains both these things. As a consequence, this defines a good cover of the space of Tame paths. And this good cover, this is not an open cover, but it's not really a problem. This good cover gives a theorem that the space of Tame paths is exactly the geometric realization of the poset of cube chains. And then the space of all paths is also homotopical equivalent to this. A few words about what is this mysterious poset of cube chains. So when you're considering Euclidean complexes, the most important example is the standard cube. And in this standard cube, the chains are exactly ordered partitions of the set of directions of your cube, or is the same as a phase lattice of n-1 dimensional permutahedral. So there is a nice geometrical representation of your spaces. And in general, if you have an Euclidean complex, then the space of paths on this Euclidean complex is just a subcomplex of a permutahedral. So you have a nice combinatorial description. And out of this combinatorial description, you can proceed any further. You can use, for example, discrete Morse theory, and there is a nice algorithm which allows you to calculate, for example, homology of the spaces using this discrete Morse theory. And this algorithm allowed to reprove the theorem of Martin Rausen and Roy Meshulam, which says what are homology groups of the space of some k-skeleton of the full cube, or even kind of full skeleton of a rectangle. So this is a k equal configuration space of sequences of points on the real line, and this algorithm is so efficient that you don't need to use computer to get this result. It's just you just read the critical cells and so on. And what about general case? Now assume that we are not living in the Euclidean complex. Our precubical set is just an arbitrary precubical set, and we need to upgrade our definitions a little bit to get meaningful results. So first, the wedge cube is just a sequence of, it's just a precubical set, which is produced out of standard cubes by identifying the final vertex of some cube with the initial vertex of the next cube, and you identify it again with the next cube, and so on. You consider it as a bipointed precubical set. You remember the starting point here and the final point here, and you can define cube chains on precubical sets just as a precubical map from cube wedge to your complex, which is exactly the same definition, but only reformulated. You don't want to talk about sequences of cubes satisfying something, you want to talk just about maps. And but introducing this definition doesn't solve all the problems. If K is not a Euclidean complex, then your covering with Tame paths lying in cube chains is not in fact covering. The maps related to inclusions of cube chains are not injective. Every path can have many presentations which use the same cube chain. And so using the poset of cube chains is no longer enough. You need to pass cube chain categories. And the cube chain category is defined in a very natural way. So objects are cube chains. It means precubical maps from one cube wedge to our complex. And morphisms are commutative triangles of bipointed maps. This gives a nice category. And this category, the geometric realization of this category is exactly the space of Tame paths, and it means that it's exactly up to homotopy the same as the space of all paths. So now let's try to understand this cube wedges. Cube wedges in itself also forms a category, which is the same as a category of cube chains over the final precubical set, which follows from a categorical abstract nonsense. And so it means that there is a combinatorial structure on the category of cube chains. It can be regarded as a presheaf over the cube wedge category. And because the cube wedge category in itself is a kind of, as a structure, permutahedral structure. So it's isomorphic to the category of faces of permutahedra. What you get is that your cube chain complex is exactly kind of permutahedral complex. The elements of your points of your execution space are glued out of permutahedra in the way as simplicial complexes are glued out of simplices, or precubical complexes are glued out of cubes. You just get a little bit complicated of polyhedra. And the final part of this interesting, what's the execution space of the final precubical complex? And there is an answer. So using this model, we were able to prove that the space of directed paths on the final precubical set is a homotopy equivalent to the disjoint union of configuration spaces of points on the real plane, which is a little bit mysterious result. And I don't really understand what does it mean in practice. As a consequence, this is an Eilenberg-MacLane spaces, or the disjoint union of Eilenberg-MacLane spaces. The fundamental group of every component is a group of braids of n strands, and that gives some applications. You get some invariants defined on your space of directed spaces, of directed paths. For example, homotopy fundamental group has a representation in the braid group. Or you can pick an element in the cohomology of the braid group. You can put this element back as an element of cohomology of your path spaces, and this way you get characteristic classes of some kind. What these invariants mean, I have no idea, but maybe they have some meaning. But on the other hand, they answer the question which was asked at the very beginning of this conference: what's the relation between computer programs and nodes? So this is one of possible relations. Well, computer programs have invariants which are made of nodes. Okay, that's first part of the story. And now I'm going to approach the same problem using different methods. This time I want to use combinatorics and some tools coming from concurrency. So let us recall what's a transition system. The transition system is just a directed graphs, and there are some labels on edges. Every edge has some letter from the alphabet. Alphabet is fixed once from all. You can take one letter of alphabet and you will go back to what happened before. Automaton is just a transition system in which some vertices are marked as start vertices and some vertices are marked as exit vertices, and we're interested in sequences of vertices which run from the start vertex to the exit vertex. And then you can ask what are possible words we obtain this way. You just remember the letter at every arrow, you get a set of words, and it's called a language of your automaton. And it's very classical and very well understood. And one remark, what are words in our world? Words are sequence of things what happened. We think of letters of some events. And what's the restriction here? If you have two events, either the first event happened first or the second event happened first, there is no situation where both events went in parallel. It's very convenient when you write, because letters are put in a sequence. There are no letters in parallel, but we could probably like to write things that happen in parallel. So the generalization of automata to the concurrent world are higher dimensional automata. So higher dimensional automatons, the precubical set with some labeling of your vertices, and there are some states which are start states, and you have some exit states, and there is some condition which says that the labeling is coherent. So let me recall, the precubical set is also some sequence of sets, and apart from that, there are some maps between these things. Well, after all, this definition became too complicated to handle, and well, we want to find a better one. So I will spend some time reformulating definitions, and after making a lot of reformulations, I will give you some definition which I'm happy of. So let me recall. A preshift is a functor from some category to the category of sets, a contravariant functor. With every preshift, there is a connected element category, which objects of this category are elements of the values of your preshift, and the morphisms are given by the operation of the preshift on this object. And there is a canonical projection. In fact, there are two ways of thinking about preshifts, either as about contravariant functors to the category of sets, or via element categories and this projection factor. So I will switch between them. And maybe you're not very familiar with preshifts and this way of thinking about things. So I will give you some examples. If you want to consider only directed graphs. So directed graphs are preshifts over such a category. Sorry, not yet. Vertices are values over the empty set. Edges are values over one. And for every edge, you have two vertices. And these vertices are encoded in the maps going from 1 to 0. When you want to model transition systems as preshifts, you have the empty set as an object of your category. This will represent vertices, then elements of your alphabet, and over every element of your alphabet, over every letter lies the set of edges which are marked by this letter. So for example, like here we have a transition systems to the left and the underlying category G sigma to the right and the element category up and some morphism of this element category. This is exactly a pre-shift. What's an advantage of using of thinking about transition systems using this kind of thing? The advantage is that in some sense vertices and edges became the same kind of object. Okay, we have a set of objects which is divided on families, a family of vertices or family of green edges and a family of red edges, but they are basically, they can be compared somehow. And another reason is as we don't want to consider only one-dimensional edges, we need higher dimensions. It will be convenient to gather all things in the single object. So I'm going to define a category, and the pre-shifts over this category will be precubical sets or high-dimensional automata. So the first thing is an LO set. I'm looking for a better name. It's just meant labeled and ordered set. You have a set with labeling, and it's also always totally ordered. Maps are preserve ordering and preserve labels. Because it preserves ordering, all such maps are injective. And every LO map is determined by the codomain of this map and by the subset of elements which don't lie in the image of your map. So, but LO maps are not exactly the maps we want to have. We have to enrich our LO maps to precube maps. In the precube map is an LO map, but additionally you make division in the set of elements which doesn't lie in the image. So all things which are not in the image are marked either 0 or 1, or they are put in the set A or set B. And there is some natural way of defining composition, which is maybe the best is to define things by an example. So you have an LO set U, an LO set V, and a map from U to V. And this map sends A to P, B to R, and there is an extra element Q, which doesn't lie in the image. So we have to decide either we put 0 or 1 here. So we have decided to put 0 at this map. And there is another map from V to W. There is some inclusion of V to W, but there's also 2 extra elements, S and U, and we have decided to put 0 at S and 1 at U. And what's the composition of these maps? It's just a composition as a composition of functions. It's obvious that we have to put 0 here. It's obvious that we have to put 1 here, but it's not obvious what to do with V. It has to be marked either by 0 or by 1. But this element V came from element Q, and there is 0 at Q, so we put 0 here. So it's just a combinatorial play, but what we have defined is exactly the precube category. So the precube category has LO sets as objects, precubical map as morphisms, and there are 2 distinguished family of morphisms. Morphisms which put 0 everywhere are a kind of lower faces, and they are called fourth morphisms. Morphisms with all ones are called back morphisms. And a precubical set is just a pre-shift over this precube category. And how do we think about precubical sets? So if you have some cube X which lies in your precubical set, geometrically it's a cube with directions given by elements of related allow set. The lower face is just taken by taking delta 1 at the suitable coordinate. The upper face is given by delta 1 and the given element. There are also operators which remove many elements of your set. And some of these elements are converted into 0, so you get lower face at these directions, and some are converted into 1, so you get the upper set in these directions. So you have again the picture like before, but there are some extra operations which are iterated phase maps. But from the point of view of concurrency, X is just a state which has a list of active events. And there are operations which allow you, for example, to terminate one of these events and pass to a state in which this event is already terminated. So it's just delta 1. And there is operation delta 0, which is an inverse. So there are terminological problems with this inverse, because the inverse of terminating is unstarting. You pass to the state in which the event didn't even started. But, well, starting is not a good thing here. So there are operators which terminate some things and unstart some things. This all gives you, again, the precubical set. And what is higher dimensional automaton? So you need to define the start cells and accept cells. So we have a cell category, which is the category of elements of your presheaf. And the higher dimensional automaton is just a precubical set with some distinguished cells, elements of the cell category, which are start, and some distinguished elements which are accept. And your HDA is simple if you have only one start and accept cell. You can define the standard cube using this way. Well, I'm not going to make much comment. There are some formulas. And finally, what are executions of HDA? So again, there is a definition, which is basically the classical definition due to Pratt, I believe, that the execution of a HDA is a sequence of cells and a sequence of phase maps, so that either you come from the lower phase to a cell, or you come from the cell to the upper phase. So there are two kinds of operations, but they are not allowed. They are both allowed, and your executions are just sequences of such things. There is a relation between these executions. Usually you talk about homotopy between paths, but there are two different relations here. One is the equivalence of paths, in which you start one event and then start another event. And it's the same, it's equivalent to starting these events at the single step. And there is an operation of subsumption. You can start some set of events, then terminate some disjoint set of events, and it's more general or subsumes the sequence in which you terminate events first and then you start events. So let me give you an example of the picture. You have a path. It starts at x0, then you start A and C, both green and red event. Then you terminate A, you start B, and terminate C. At the end of your execution, B is still active, but we allow this kind of executions. And the second execution is equivalent. This time we don't go from x0 to x1, but we travel through y. So it means that we start A and star C, and both these things should be equivalent. We don't care about which happened first. And finally, the last example, it starts exactly as alpha, this last path gamma, but at the very end, when we travel from x2 to x4, we first go to the vertex z, then we go to x4. It means that first we terminate C, and only after we start B. This is execution which is homotopic, but it's not equivalent, it's more specific. It's somehow contained in the path represented by alpha. And again, this is a classical definition, but we are not happy with this definition of path because it's difficult from the combinatorial point of view. You have some sequences of simplices, some sequences of formats. It's not convenient. So let me introduce again some formalism. What is a directed category? We talk about directed spaces, so there should be something which is called directed category. So the directed category is just any category with two wide subcategories. And the category C0 is subcategory contains fourth morphisms, and the subcategory C1 contains back morphisms. And because they are wide, identities are both fore and back. And yeah. Excuse me? A wide subcategory, it means that contains all objects. I could require that. I don't have to. Yes, this definition, I didn't give this definition to make research of directed categories. And this, from this point of view, this definition is incomplete. Yes, you should give more axioms to make a good notion of directed category. I just want to use this definition, use this to define something later. Okay, so I want to say what's a directed categories, category two subcategories in which identities are both belong to both. And I need three examples. So the category, precubical category, is directed because it has some fourth morphisms, D0, and some back morphisms, D1. Of course, the cell category of every precubical set is also directed because in the cell category, all morphisms project to the precubical category. So if your image is 4, then your morphism is 4, and vice versa. And the third example is an interval. Linear category plays a role of interval. It consists of a sequence of objects, and between any pair of objects, either you have a fore morphism going right or a back morphism going left. Okay, and this way you can define a path or HDA just like a directed functor, which comes from the linear category to the category of cells. And what's a label? Label, you want to somehow say what's the meaning of your execution. So you start first with your path. Then you project to the precube category. Here you can read what are exactly the events. Then you want to somehow glue up these things together. What is gluing up things in the category theory? It's just taking colimit. But it doesn't make sense to take colimit in the precube category because it's too small and stupid for such things. So you pass again to precious. And you know that in pre-shift category, you can take all colimits you want, and the result is somehow well defined and unique. So it's a label. Okay, again, the label of a path is some other precubical set. You say what is the first element of your precubical set and what's the last element of your precubical set. It gives you a simple HDA. And well, there is a very limited number of HDA which could be obtained this way. So the defining a label makes sense. And this kind of objects I should conclude very fast. This kind of object I will call this kind of HDA track objects. So track objects are all objects which are defined this way. Instead of paths, you can use also tracks. You can tell your execution is just a map from a track object to your HDA, is a precubical map. And there is an equivalence between tracks and equivalence classes of paths. So it's even more convenient, even if more abstract way of defining executions. And track objects form into two categories, because you can compose, you have a lot of operation. So objects of your category are just LO sets, or we can think about them as just standard cubes objects. Morphisms from LO set U to LO set V is just a track object which starts in U and ends in V. It means the starting cell has a kind U and the terminating cell has kind V. You can compose tracks by gluing them together. You take two tracks, you put the final cube here and the initial cube here, then you take colimit, glue them together, you have a new object. There are two morphisms. Two morphisms are easier than one morphism. Two morphisms are just maps of HDA. And this operation corresponds to taking subsumption of paths. And of course, composition of two morphisms is the same. So in the similar way, you can define a track complex of precubical set. This time, objects are cells of your precubical set. Morphisms are possible tracks starting from one cell to another cell. You can concatenate these tracks together, and you have an extra two category which is defined by subsumption or inclusion of one track to another track. And it gives you something, this track complex. It's not just sum to category, but it's in some sense a pre-shift over this standard category of track objects. Okay, it seems very complicated up to now. So the last thing I want to do, I want to understand what are track objects. And the two category of track objects is isomorphic to the category I will describe now. So the objects of this category are again LO sets. The morphisms of the category are called ipomsets. So ipomset is just a partially ordered set with some labels. There is a precedence order which is important. It means that one event happened before, then another event. There is some additional event order which has a kind of technical meaning. And there are so-called interfaces, S and T. So some objects, some minimal objects of P lie in the source interface. We think about this, that these events are already running when you start to be our execution. And the same with target interfaces. And then we restrict to interval ipomsets. It means that poset is interval if it has interval representation. And here we have an example of ipomset. You have elements and labeling, which is meant with colors, and thick arrows mean precedence, but there is an X-ray event order, and there are source interfaces, target interfaces. And on this ipomsets, you can define a serial composition. Like in the picture, you identify terminating interface and source interface with each other. You can glue ipomsets this way. There is an operation of subsuming ipomsets. So ipomset is more specific. It has, if it has more precedence order and less event order. And finally, we can define the two categories of ipomsets using this operation of concatenating posets and subsumption. And finally, this mysterious category of track objects is isomorphic to the category of ipomsets, which is described in this relatively accessible way. So it's time for conclusion. So on one hand, we have defined the track complex, and the cube chain category, which appeared before, lives in the track object, yes. And as a full subcategory, so you can restrict your track complex to this cube chain complex. And the Tame theorem means that by making this restriction, you don't change anything. So there is a Tame theorem at this level. You can restrict from the category of interval ipomsets to the category of some even smaller category. So, okay, maybe I won't talk about this. Time is over. Thank you for your attention.
Just a quick question. Yeah.
So your Tame theorem is what connects both parts of your talk, right?
Yes. Yes.
Okay, I need to understand. Thank you.
Another very quick one. So I just should say that I remind you that I have opened a shared Google document. So I have some questions to Krzysztof, but I did put one on the Google Docs so that you have to look at that.
Oh, I have to check it and then put an answer.
Minor thing about the representation, but I'm interested in that in things. So in case to use that to connect to speakers. For this morning, it's been a real mess. Sorry about that, but then you can still use that for later discussions. And another last very quick one. Okay, thanks. So let's go to lunch and thanks.